Hey, what's up, guys? Welcome back to Mathematical Toolbox. Today we're going to be solving some stochastic differential equations using the variation of parameters method. So I apologize for the lack of videos on this series. A bunch of stuff's happened. I accidentally deleted the footage, then lost the pen that I use for this little tablet to make these videos. So yeah, that's why it's been so long. But regardless, if you have been keeping up with the series, you can skip on over into the next chapter. And if not, then you might want to listen to the rest of this little intro here. So, our primary objective again is to have some fun and identify and solve certain types of SDEs. We are going to just be crunching some numbers essentially, right? It's going to be very similar to like a first undergraduate course in ODEs, right? Just computational. We're not going to really be getting down into the dirt with what exactly we're doing and all that kind of technical stuff, right? We're just going to be crunching some numbers, right? And you need to see the previous videos in the series and haven't verified these SDEs for existence and uniqueness or any of the other things people usually care about in practice, right? Now, if you want to learn this subject on your own, this is my first recommendation here. This blue book here by Ovidio Galin. So Professor Galin does some really good stuff with this subject with this book here. It's an amazing book. All you need is Cal 3 to read this book. And this one down here, it's intended for scientists and engineers that need the content, right? So you need some background with some probability and statistics, or just like statistics, anything that you would have picked up from like a book like BOAS, maybe on math methods, that kind of stuff. And with some other background that you would have picked up from like your science and engineering courses, that'll be sufficient here. This yellow one down here, though, you do actually need a dedicated course in probability undergraduate to read this book. It is at a more technical level than this blue one here and this red one. It's probably about the same as the red one, to be honest with you, but it does have more of a focus on proofs and theorems and that kind of stuff, right? But it does have quite a bit of applications, and it's still a very serious math book. And this one on the upper right hand corner is probably the most technical out of the three. At the bare minimum, you should have some analysis, linear algebra, calculus, differential equations, all of that stuff, right? Probability as well. Ideally, you should even have some measure theory as well, right? That's ideal. You can try reading it without the measure theory. There are some measure theoretic arguments used in the book, but you can try without it, see how far that gets you. But I really strongly recommend some probability and some analysis at the bare minimum, and you can try maybe unsuccessfully so from there. We have partial solutions and all but this red book here, so don't recommend that red book. But let's go ahead and move on here. Already going forward, I'm not going to show the general case. Shout out to Jan on Twitter. Jan had mentioned that sometimes or I guess all the time, the general case seems more complicated than the actual method or than what the method actually entails. So we're just not going to show it. He had mentioned that I should, or suggested that I show it at the end. We're just not going to show it. Let me know what you all think. So let's go ahead and get started here. First thing we want to do here is treat this like it were an ODE. So we send the xt over the other side. We have something that looks like this, right? And we solve it again like it were an ODE. So ln xt equal to alpha wt plus some constant. And this constant is a function of t. And we want to isolate the xt. And we get something that looks like this. And from here, what we can do, and I'll do it in the next example or the following example, we can actually bring this xt down so that our solution looks like this. But I won't do this. I won't talk about this yet. We'll just ignore this for now. We'll just leave it as it is here, and we'll work with it like this. So next thing we want to do here is take the derivative of our solution here. And my advice to you here is to do it this way the entire time that you practice with this method, right? So for instance, if we leave the deterministic term outside and then apply the differential operator to the stochastic term, then let's do it like this every single time, right? Or if we write the stochastic term first and then apply the differential operator to the deterministic term first, then do it like this all the time. Trust me, it'll be so much easier for you because you'll be able to notice when you make mistakes. So let's go ahead and just continue working through this. So we have okay, so from this step to this step, all I did was apply Ito's chain rule, and we get from this term right here, we get these two terms, again, multiplied by that e to the c, and I just rewrote this e to the alpha wt from up here. I took the derivative of e to the ct, which is this term right here, with this dt, and now we can move on. And from here, what we want to do is find where we can actually make a substitution for our original solution, right? So our solution was xt equal to e to the alpha wt plus c. And we want to see where we can make the substitution back into this equation here. And recall that this is actually our original equation, right? Our original problem, our SDE. So we can make a direct substitution here, and we have the same thing, equal signs on both sides. We can go ahead and cancel these out. And I'll just go ahead and show you this for yourself, right? So we have alpha xt dwt equal to dxt, right? This is our original problem, our original SDE. So we're just making that substitution here, and we can cancel it out with the left-hand side, the exact term, right? So the exact same term. So now we have 0 equals to xt. We're going to just group these terms, the two terms that are left, plus the first derivative of c dt, and we can just get rid of this xt term and integrate. So this is our solution for c. And from here, what we can do is go ahead and retrieve our original value or our original solution, right? Which was xt equal to e to the alpha wt plus c of t here. And now we have derived the value for t, or for c rather. So let's go ahead and just plug that in. And we need to make the substitution for e to the k is equal to x naught, which is equal to 1. This is our initial condition from earlier. So we have that our solution is e to the alpha wt minus alpha squared t over 2. And this is our solution here. Our final solution is what we needed to show. And this is exactly what we have here, right? So this is our initial condition, x naught equal to 1. And we're done. That's it. That's the end of the problem here. So this is our next example here. It's pretty simple. We do it in the exact same way. So we divide our SDE by xt. And then we integrate. And we isolate the x. And as we did before, we differentiate the solution. And again, here we have to use Ito's chain rule. So let's go ahead and do that. Now we can just try to multiply these terms through and make substitutions for our original solution, xt. So all we did here is just make the substitution for our solution, right? The one that we had derived earlier, which was xt equal to e to the sigma wt plus mu t plus ct, like this. So all we did was just make the substitution, right, for xt. And from here, what we want to do is plug in or find a way to plug in our original equation, right, the SDE itself. which looked a little something like this term here with this term with this dt, right? So let's go ahead and break up this final term, this third term on the right-hand side and put it in a nice form so we can make a direct substitution. So let's go ahead and reference our original problem. So it was mu xt dt plus sigma xt dwt, right? So let's go ahead and verify. And that looks exactly like what we've got here, right? So again, this is dxt. We can cancel this one out with this one on the left-hand side. So we can actually group these together. Let's go ahead and do that. By the way, I did make a mistake here. So we do have to put an xt right here. And this just comes from not multiplying this xt through, right? So now we're all caught up where we're supposed to be. So let's go ahead and just bring this together. And from here, we get rid of the xt, just divide it out, and we integrate. And again, this is the value of our arbitrary function here, c of t. And now we can get our original solution once more. With that value of c, where e to the k is equal to our initial condition. So finally, our solution is e to the sigma wt plus t times mu minus sigma squared over 2. So this is the final solution here. We are done, and now we're going to move on into our third and final example here. So we have to verify that from here, we get this one. So we get an integral here as our solution, right? So we're going to have to do something a little bit different here, since if you notice, we actually don't have an xt term here with this beta term with our stochastic term, the dwt, right? We don't have an xt in there. So we have to do something a little bit different. So what we're going to do first is actually break this problem up. We're going to ignore the dwt term, and we'll deal with it later. So let's go ahead and solve the rest of the problem without that dwt term. Same thing here, right? Divide by xt, and the rest is easy. So this is where it becomes a little bit different. What we're going to do is bring that c of t down. So I'm going to denote it by a capital C here. We have capital C of t times e to the negative alpha t. Same thing, we take the derivative of this term, our solution. And again, we want to make a substitution, right? Remember, our solution look like this. So looks like we can plug that in right here. So let's go ahead and take a look at our original equation, the SDE, right? So here we have dxt equal to negative alpha xt dt plus beta dwt, right? So what we want to do here is, you can just make the substitution already, but I like to send everything to one side so that it's a little bit easier to visualize, right? So let's go ahead and send the negative alpha xt dt over to the left-hand side, and we can make a substitution for beta dwt. Again, so let's go ahead and reference our original equation again. All I did was send this alpha xt term over to the other side, and then I made the substitution for beta dwt. So now we have beta dwt equal to e to the negative alpha t dc of t. And let's isolate this term right here. And integrate. So from here, we go back to our original solution, which was what we want to do is solve this for C of t, which is going to give us C of t equal to xt e to the positive alpha t. We want to plug this in here. Then we isolate the xt. Then we use our initial condition, which was x0 equal to 0. So this term is going to disappear. We have xt equal to beta times the integral of e to the alpha s minus t dws from 0 to t. And this looks like what we needed to show, right? Beta integral 0 to t e to the alpha s minus t dws. And yeah, that's it. We're done. We are done with this problem. So you can find expectations and variance if you are interested in doing so, but I'm not going to ask you to do that. So this one's pretty much the same up until the point that we get to this part, right? So we have xt, or 0 equal to xt times the derivative of that constant plus some other term, some function of t, or in this case, it'll be a wt. And from here, again, we get rid of that xt. And what I was doing earlier was I was just giving us an arbitrary constant, right? So when we go to solve this, we get something that looks like, again, the integral of this plus some constant. But here, what you want to do instead, because again, we're going to have a stochastic term inside of this integral, and this isn't very well defined. So to avoid this nonsense, what you do is you just add some limits. And we get that our C of 0 is our initial condition. In this case, it's going to be 1. Right, so that'll pretty much get you to where you need to be with this problem. So that's the only difference. That's the only difficult part here. That's the only part that actually changes. So the rest of that should be very simple for you, more than likely. And it was the square, not just a regular running motion. It was the square. And yeah, that's pretty much it, guys. Hope you enjoy that. So now I want to circle back a little bit to the situation that we had earlier, right? So when do we know when to use, let's just say, this or this one here? When you had that situation that we had, and I think it was example 3, right? Yes, example 3, that's when you want to bring that constant down. You can bring the constant down in the case of example 1. It's just going to be a little bit more work, but you get the exact same solution. So this is our first example here. You can definitely, again, bring this down so that our solution looks like this. And you can solve it the way that we did in example 3. You can do it that way if you want to. Again, it's just going to be a little bit more work for you, but you get the exact same answer. And not worth it. But for sure, when we have the form that we have here in example 3, that's when you want to bring that down, that constant down. I tried bringing that constant down in the case like example 2, which was this one here, and it kind of just didn't work out. It's possible that I made a mistake, but it's really not something that I cared too much to explore, to be honest with you. And we're all just here to have some fun anyways. If you want to question me some more about it, and you're trying to have some difficulty, you're trying to explore it more, I can help you. But again, it's not something that I particularly care too much about. Unless one of you is going to ask me for it, then I'll definitely help you out if you are interested. But again, this is just a little bit of further discussion on when to bring this CFT down. Again, when you have something like equation or example 3, then you want to bring that CFT down. Try solving it without it. You're going to have a hard time. You can bring it down even when we don't have a case like 3. When I tried it out in example 2 with that equation in example 2, didn't work out so well. So just a little bit of further discussion for you guys if you're interested. But that'll do it for this one. Hope you enjoyed this video. Hope you enjoyed these examples as well as this method. Let me know if you have any difficulty with this problem, this exercise. Hopefully not, but I'll respond to you pretty quickly. If you do, thanks for watching, guys. See ya.